All right, let's talk about the invisible architecture that powers literally our entire world. It's the system that runs behind the scenes in everything from massive industrial plants to the very device you're watching this on. We're diving into balanced three-phase circuits.
You know, it all starts with a really simple question. Have you ever been driving down the road, looked up at those giant high-voltage transmission towers, and noticed that the wires almost always come in sets of three? Well, that is definitely not a coincidence. It's actually the first clue to an incredibly powerful and efficient piece of engineering.
The answer, and it's a really cool one, has to do with something called balanced three-phase voltages. And this isn't just some technical term. It is, quite literally, the foundation of our entire modern electrical grid. It's all about an elegant balancing act.
Okay, so what does that actually mean? Well, think of it this way. We're generating three perfectly identical waves of electricity. They all have the same strength, that's the amplitude, and they all have the same rhythm or frequency. But, and this is the absolutely brilliant part, they are intentionally knocked out of sync with each other in a very, very precise way.
And that precise offset, it's not random. It's exactly 120 degrees. That is the magic number here. Each of the three voltage waves is perfectly out of sync with the others by exactly 1/3 of a full cycle. Imagine three runners on a circular track, all starting at equally spaced points, all running at the exact same speed. That's kind of what's happening here.
So what happens when you set them up like that? Well, this is where the magic really kicks in. At any single instant, if you add up the values of the three voltages, the sum is always zero. Always. As one wave is hitting its peak, the other two are in a trough, and they just perfectly cancel each other out. This creates an incredibly stable, perfectly balanced system.
Now, the order in which these voltages hit their peak, that's a big deal. It's called the phase sequence. You can have an ABC sequence, or you can have its mirror image, an ACB sequence. And this might seem like a really minor detail, but trust me, it is absolutely critical. If you get the phase sequence wrong, you could make a huge industrial motor spin backwards. Not good.
So we've got these three perfectly balanced voltages. Awesome. But how do you actually hook them up? How do you physically connect them from the power plant to all the things that use the power? You need a wiring diagram, a plan. Turns out, there are two main ways to wire this stuff up. Think of them like two fundamental types of Lego bricks for building power circuits. You've got the Y or Y connection and the delta connection. The Y looks like a star. It has a central neutral point. The delta, well, it looks like the Greek letter, a closed triangle. And you can use both of these for the source and for the load. Now you might be thinking, analyzing a full three-phase circuit sounds like an absolute nightmare. And you'd be right, it can be. But engineers have this fantastic little shortcut that makes it surprisingly simple, especially when you're dealing with the most common set. And here is that beautiful shortcut. When you connect a Y source to a Y load and the whole system is perfectly balanced, something amazing happens. That neutral wire in the middle, it carries absolutely zero current. Nothing. And if there's no current flowing through a wire, you can basically just ignore it for your calculations. This is incredible. It means we can understand the entire complex system just by analyzing one single simple phase. And that, right there, that's the key insight that just simplifies everything. An engineer can solve the circuit for phase A, and because the whole system is perfectly balanced, they instantly know the answers for phase B and phase C. They're just the same values, but shifted by 120 degrees. It's a massive time saver. Okay, but what if your load is a delta? You're not stuck. Engineers have another clever trick up their sleeve. They can mathematically convert any delta connection into an equivalent Y. There's a really simple formula for it. This lets them pretend the delta is a Y, so they can use that exact same powerful single-phase shortcut to figure it all out. Okay, I want you to burn this number into your brain, the square root of 3. It's about 1.732. This thing is going to pop up everywhere from here on out. It is the magic constant that connects all the different pieces of a three-phase system together. Seriously, remember this number. And just like I said, here's where that number shows up. This table basically shows how root 3 is the magic conversion factor that links what's happening inside a single phase to what's happening on the main power lines connecting everything. See, in a Y connection, the line voltage gets a boost by a factor of root 3. In a delta, it's the line current that gets the same boost. It's the key that governs the whole system. Okay, so we've talked about what a three-phase system is and the clever ways engineers analyze it. But the biggest question is still just hanging there. Why? Why go through all of this trouble with 3 phases instead of just sticking with one? Well, this is the grand payoff.
And here it is, the answer. See, the single-phase power coming out of your standard wall outlet, it's not smooth. It actually delivers power in pulses, dropping to zero hundreds of times every second. But in a balanced 3-phase circuit, the total power being delivered is perfectly smooth. It's rock solid, constant. It never drops, it never wavers. And that is a huge, huge advantage.
And that smooth, constant power delivery is exactly what big, heavy-duty motors need to run efficiently, and without a ton of vibration. And of course, if you want to calculate exactly how much power the system is delivering, engineers use formulas just like these. And look who's back, our old friend, the square root of 3, right there in the heart of it all. And this whole balancing act is super important in the real world. Big motors can sometimes pull on the grid in a way that makes the system less efficient. So what do the utility companies do? They install these huge banks of capacitors that act like a counterbalance, supplying a different kind of energy that helps keep everything running smoothly. It is all about maintaining that perfect, constant power flow for every single customer. So yeah, those 3 wires you see strung up on towers everywhere, they're not just wires. They are a testament to an incredibly elegant solution. They make sure that the energy our modern world is built on flows in a balanced, efficient, and constant stream. It's a pretty amazing system when you think about it. And it kind of makes you wonder, if 3 phases are this good, what comes next?